Alright, so we are going to start with Chapter 2, talk about representing motions. We're going to split this into two sections. First, we're going to talk about particle diagrams and distance-time graphs, and then we'll talk about velocity. Okay, so let's first get into Section 1, which are position-time graphs. Okay, there are all kinds of motion. When we talk about velocity, we're going to talk about motion. And when an object is in motion, its position is changing. This could be a straight line. It could be a circle, an arc, back and forth, whatever. Its position is changing as it is in motion. Okay, well, motion is also relative. And what this means is that, let's say we have a book on the table. Well, we would say that it's at rest relative to the table. But in actuality, because Earth is moving and the book is on Earth, it's moving in relationship to the sun at about 30 kilometers per second. So this is how we say motion is relative. I'm sitting here still in my seat, but I'm really moving at 30 kilometers per second in relationship to the sun, and so are you. So we can put motion into several different visible forms, and one of those is a motion diagram. It's basically a series of images that shows the position of the moving object at equal time intervals, and that is the important part here. That we're showing it at equal time intervals. So for example, let's take a look at this motion diagram down here. Forget about letter A, I don't know what's going on there. Okay, so here we're covering an equal amount of distance for every equal time interval. We would say that this is constant speed, or constant motion, because within each equal time interval, the same amount of distance is being covered. Okay, so now let's look at letters C and D. And what I would recommend that you do is maybe pause it for a second, see if you can figure out what's going on with C and D on your own, and then go ahead and play, and we'll confirm. So if you want to do that, go ahead. Otherwise, I'm going to keep going. Okay, so if we look at letter C, here we have the particle, or the object. Now, the time intervals are equal, but as you can see, the distance is not. In fact, with each equal time interval, the distance is getting larger. I would say that this is some sort of acceleration. We're starting to cover more distance in the same amount of time. Okay, and we'll get into acceleration in Chapter 3. If we look at letter D, it's almost the opposite. Here we have a very large distance being covered, and then as equal time intervals go by, we have smaller and smaller distances. And so I would say that this is deceleration or negative acceleration. The other type of diagram we can have is a particle diagram. This is showing the object, but instead of drawing, little stick figure people or cars or whatever it is that's in motion, we're just going to use points. That's my type of diagram because stick figure is about all I can draw. Okay, so if we look at the top one, here we have constant speed. Our dot is occurring with equal distance, and then we've got equal time intervals. So again, see if you can figure out what this one and this one are representing, maybe based on what we talked about for the motion diagram. So if you want to pause, you can go ahead. Okay, otherwise we'll continue. So here we've got a smaller distance, larger, and the distance keeps getting larger with the same amount of time. So I would say that this is acceleration. And here we have the opposite. Large distance, and now our distance being covered is getting smaller, and so I would say that this is deceleration. Okay, so we can take that information about motion, we can put it on a motion or particle diagram. We can also graph it. Before we get to that, let's talk about the points of coordinate system. We have the origin. This is the point at which both variables have the value of 0. So if this was our graph, we would say that this was the origin. Okay, position on this type of graph is the separation between an object and the origin, or where it's basically where the arrow points. So if there's my arrow, here's my object, here's my origin. Okay, this is the position. And then the distance is how far the object is from the origin. So we could measure this there, and that's our distance. Okay, so we drew an arrow on our graph, and we're going to be graphing motion. Well, there are kind of two types of arrows, or two types of things we can talk about here. So a vector involves the magnitude, or the amount, and the direction. Some examples of this would be velocity and displacement. The other type is a scalar. A scalar does not indicate direction. So this would be speed and distance. So speed, and we're going to talk about this in more detail in a minute, is meters per second. So let's say you're going 30 meters per second. For velocity, we would say you were going 30 meters per second north. And so we've also indicated a direction, whereas a scalar does not. Both scalars and vectors, however, can be added. And when we do add those, we can get what's called a resultant. And it's basically the vector that represents the sum of two vectors. Now, eventually what we're going to get into is everyone's favorite, trig and triangles. And so this is what we would call the resultant. Using Pythagorean's theorem, we can add vectors that are in opposite directions. If we have vectors that are in the same direction, for example, maybe a plane experiencing a tailwind, then these would add together. Let's say we had that same plane experiencing a headwind. Technically, they're still adding, but this one is going to be negative, so our overall resultant is going to be less. Okay, if we want to graph velocity, we need time and displacement. So a time interval is, a time period over which something occurs. And so this is the difference between two times. So we would take t final minus t initial, that's what the F and the I stand for, and that would give us our delta t, or change. Delta means change. The other thing we need is position. So this is a vector with its tail at the origin of a coordinate system and a tip at its place. So here's our vector, here's our origin, and then this is where the object is located. Now displacement is the change in position. So again, just like we had time interval was the change in time, displacement, we're going to take our final distance minus our initial distance, and that gives us our change in distance, which is, again, the triangle or delta. Okay, so we can take all this information and put it on a position time graph. So on our position time graph, I keep losing my pen. Okay, the x-axis is time. The y-axis is position, or I'm going to put d for displacement, and we could just put t for time. The instantaneous position is the position at a particular instant. So we could just pick one instant in time. Whoops. And that would give us the displacement at that particular point in time. We can also use position time graphs to represent the motion of more than one object. So for example, here we have 4 different carts. Okay, we've got our time on our x-axis, our position on our y-axis, and you can see that some of them have more of a constant speed, and we'll talk about that in a second, and some of them have more of a quadratic. We talked about that relationship. Okay, and so I don't see any inverse relationships, okay, but we can definitely see that all 4 carts have different position versus time factors. All right. Here are some examples to try to apply these concepts. We're also going to discuss them in class. Okay, so before we get to the checks for understanding for this section, I thought that everyone might appreciate a physics joke. And who would thought that Chemistry Cat would be part of a physics joke? Well, I certainly didn't. So take a minute to enjoy this, and we're going to go on to the check for understanding questions. Okay, so for section 1, which talked about position time graphs, number 1 says, what does it mean to say that motion is relative? Number 2, explain the difference between a motion diagram that represents constant speed versus one that represents either acceleration or deceleration. Number 3, what's the difference between a motion diagram and a particle diagram? Number 4, given this example of a coordinate system, label the origin, position, and distance. Number 5, what is the difference between a vector and a scalar, and give an example of each. Number 6, how do you find the change in a variable, like how do you find delta t or delta d? What do you put into that equation? And number 7, on a position time graph, what are the 2 axis labels? So what's the label on the x-axis and what's the label on the y? All right, give these your best shot. We'll discuss them in class. Have a good day.